Beni duyabiliyor musunuz? Pardon, sesim geliyor mu?
Evet, geliyor.
Tamam. Hi everyone. It was my pleasure to work with Övünç over the summer. We spent a lot of time working on the representation theory of the symmetric groups. He is a senior student at Boğaziçi and he was very hardworking. Now we are gonna hear what he learned.
And thanks for the brief introduction. Hello, everyone. Today, I will be talking about Young tableau and representations of symmetric group. So let's see our game plan. First, I will describe what a representation is, and then I will answer the question, why do we really need representation theory? Afterwards, we will describe the building blocks of representation, which will be called irreducible representation. And then we will talk about Young tableau, which are tetris-like combinatorial tools that will help us to construct the representations of symmetric groups. And then we will talk about Specht modules, which are derived from Young tableau. And then we will finish. So let's begin. What is a representation? The philosophy behind the representation theory is that we want to add linearity into the group theory. But how do we do it? Let's see the definition. A representation of a group G is a homomorphism from group G to itself, from G to general linear group, which is a group of m by m matrices, invertible matrices, whose entries are coming from the field F. Now, there is also an equivalent definition, which is a vector space V, and we define a G action on this vector space. But as you can see over here, this first three action is general group action properties. However, the fourth and the fifth one describes the linearity of this action. I will not talk about this, but there is a one-to-one correspondence between these two definitions, meaning that if you start by taking a row representation, homomorphism, then you can construct a corresponding FG module V and vice versa. So let's answer, do we really need representation theory? And the answer is obviously yes, but why? First, consider these two important theorems, which are highly significant in advanced group theory. Also, there's Fermat's last theorem, and which is highly trending still now. The proof of these all three theorems consists of representation theory, and we still don't know that if there are proofs without representation theory. So the answer is obviously yes, because we need to use these theorems. So let's continue. Let's give a concrete example of a representation. And as I said earlier, we will work about symmetric groups. And here's an example of a symmetric group, representation of a symmetric group. I just write the map here from S3 to GL3C. And you need to check the homomorphism, if it is homomorphism or not. But I will not do this. You can check it by yourself just by taking two elements of S3, multiplying them, and look at the image under this map. But as I said again earlier, there is a one-to-one correspondence between the definitions. So if we have this homomorphism, then we also have to have a FG module vector space. What it is? It's this vector space U with the basis elements V1, V2, and V3, and the action of S3 on this vectors is given by here. GVI is G acts on VI by the action in the index. So here's an example. Let's take V2 and let's take the transposition 1, 2. 2 is mapped to 1 in this transposition. So 2 will send this, 2 will be mapped to 1 and we will get V1. And this U has a geometric interpretation. It is a three-dimensional vector space. So you can regard it as R3 Euclidean space, and you can consider this basis elements as a natural basis, and S3 permutes these basis elements. So in conclusion, whole Euclidean space is closed under S3 action. By the way, we will be using this example U later in the presentation, so keep in mind that example. Now, what is a sub-representation? We was talking about V, which was a vector space. So in order to define sub-representations or equivalently submodules, we have to consider its subspaces. take, for example, W. We said that W is a submodule if it is closed under G action. Let's give an example, W1, and W1 is a subspace of U, which is spanned by V1 minus V3 and V1 minus V2. It is closed under S3 action. In order to see this closure, you have to check every element of S3. I will not do this, but again, I will just give an example here. Let's act on V1 minus V3 by this permutation 1, 2, 3. V1 will be mapped to V2 because 1 is mapped to 2 in this permutation. V3 will be mapped to V1 because 3 is mapped to V1 in this permutation. So we get V2 minus V1, which is equal to minus V1 minus V2. And it's one of the basis elements. So we again in the W1. Also, this W1 has a geometric interpretation in it too. If you consider these two vectors, they span a plane, and we can say that this plane is also closed under S3 action. Irreducible representations. Before defining that, I want you to remember you can obtain any natural number by multiplying prime numbers. Moreover, you can obtain any group by amalgamating simple groups via direct product or semi-direct product, etc. Because these simple groups and prime numbers are building blocks of these theories, and we have building blocks in representation theory too, which are called irreducible representations. And we say that V vector space is an irreducible representation or irreducible module if it does not have any submodules besides this zero vector space and the whole vector space itself. Now, again, let's see an example. W2, which is again the subspace of U, which is spanned by V1 plus V2 plus V3. Again, to see the closure, you need to check all elements, all at least the generators of S3, but I will not do that and give an example. Let's consider this 1, 2, 3 permutation, and let's act on this element. V1 will be mapped to V2, V2 will be mapped to V3, and V3 will be mapped to V1. So we again get the same vector. And also this W2 is irreducible. Why? Because as you can see, W2 is just a one-dimensional vector space, meaning that it does not have any subspace besides zero vector space and the W2 vector space itself. Moreover, it has a geometric interpretation too. We can consider it as a line, and this line is also closed under S3 action. Now, I want you to notice that U is the direct sum of W1 and W2. How can you see this? We can consider the geometric interpretations of these subspaces. W1 was just a plane, and W2 was a line, which is actually perpendicular to that plane. So this decomposition indeed true. Now, after seeing this submodule decomposition, one should be asking this question. Can we always decompose an FG module into its submodules? Why would you ask this? Because if so, then we can always have a decomposition into irreducible submodules. And if we have decomposition into irreducible submodules, we can work with irreducible submodules, which are smaller and they are easier to work with. So it is an important question. And how would you get an irreducible decomposition? Let's take an example of U. We know that W2 is an irreducible representation. However, we don't know if W1 is irreducible or not. We just saw that it's a submodule. Suppose it's not an irreducible, so we can decompose into its submodules, and inductively continuing, after we get an eventually we will have the irreducible decomposition. Now, I will not answer this question because it's already known by the Maschke's theorem. If there are few restrictions in G and the characteristic of the field F, this is always true. But we will answer these three important questions. How many irreducible FG modules are there? What are their dimensions? And how can one explicitly construct them? Now, with the help of the Young tableau, we will answer these three questions just for the symmetric groups. So let's first define Young diagram. This is a collection of empty boxes arranged in left justified rows with a weakly decreasing number of boxes in each row. And let's define standard Young tableau. This is a Young diagram filled with numbers from 1 to n, each one occurring exactly once, and the inserted numbers must increase across each row and increase down each column. And as you can see examples here. Moreover, there is a notion of shape, which is a tuple that records the number of boxes in each row of a Young diagram. And we can take this one as an example. And the shape of this Young diagram is 5, 5, 4, and 3. Moreover, I want you to realize one more thing. For a given Young diagram, there is no unique Young tableau, meaning that there are more than one ways to insert numbers into Young diagrams. So, what's the relation between Young tableau and representations of Sn? We have already known one, which will be followed by this diagram. The number of irreducible representations of Sn is equal to the number of conjugacy classes of Sn. This is known by representation theory. And the number of conjugacy classes of Sn is equal to the number of cycle types of Sn, which is known by group theory. And the number of cycle types of Sn is equal to the number of partitions of N. This should be obvious because the cycle types are just parenthesized version of N. And the number of partitions of N is equal to the number of shapes of N. And the number of shapes of N is equal to the number of Young diagrams with N boxes. Now, if you consider the first and the last component in this equality, you can easily infer that there is a one-to-one correspondence between irreducible representations of Sn and the Young diagrams with N boxes. So, but you should ask these questions. Which irreducible representation corresponds to which Young diagram? Because there are more than one Young diagrams and there are more than one irreducible representations. The answer will be Specht modules, and we will talk about this in a minute. And the second question, what are the dimensions of these irreducible representations? The dimension will be equal to the number of standard Young tableau, because we said that the number of standard Young tableau is not one. There are more than one ways to insert numbers into Young diagrams. So let's continue. We can also define an action of Sn on this standard Young tableau. Let's define over here. Let's take this standard Young tableau and let's act by 1, 2, 3 permutation on this. 1 will be mapped to 2, and 3 will be mapped to 1, 3, and 3 will be mapped to 1. And here, the definition of the action should be obvious. You only act the inserted numbers. But however, notice that the latter diagram is actually not a standard Young tableau. So in order to have an action of Sn, we need to have a larger set of tableaux, and which will be called numberings. Numbering is a standard Young tableau without having increasing properties. And there is another example over here, which is a numbering. And you can see that this tableau also does not approve the increasing properties. Moreover, we have to define tableaux because we will define Specht modules, and the Specht modules will be vector spaces, and vector spaces have a basis, and basis elements will be tableaux, will be defined by tableaux. A tableau is an equivalence class of numberings of Young diagram, 2 being equivalent if the corresponding rows contain the same entries. We will denote the tableaux by these curly bracket T notation, where T is a numbering. And basically speaking, a tableau is just a numbering, and you delete the vertical lines in the diagram. And there's an example of 2 tableaux here, and they are equal because the corresponding rows have the same entries. Sn can also act on tableaux, and action is given by here. Basically speaking, you just first act on the numbering and then consider its tableau. Now, we will see the correspondence between the Specht modules and the irreducible representations of Sn. Now, first, we will define these elements, VTs. These will be the basis elements of Specht modules, but there are 2 notions we are not familiar with right now, which is first CT and sin Q. This sin is a function defined over symmetric groups, and this sin function gives out 1 if the permutation UQ is even, and it gives out -1 if the permutation Q is odd. And this CT is the column group of the standard Young tableau which is a subgroup of Sn and permutes each columns of T. Now we are ready to define Specht module. Specht module is Specht module notation is this one, S lambda. S lambda is a complex vector space with the bases Vt, and you can see the Vt's over here, as T varies over all standard Young tableau of the shape lambda. Now, this is then quite important theorem. I will not prove it, but I will use it to give a concrete example. For each partition lambda of n, S lambda is an irreducible CSM module. Moreover, every CSM module is isomorphic to exactly one S lambda. What this tells us? This tells that Specht modules and the irreducible CSM modules has an one-to-one correspondence. Now, let's give an example. Let's take n equals 3. We have 3 partitions because 3 has 3 partitions, and we get 3 Young diagrams, and you can see the Young diagrams over here. We will construct this Specht modules of these Young diagrams, which will be denoted by these 3. But before constructing Specht modules, let's see their dimension, Specht modules dimension. What will we do? We will just insert numbers into these diagrams. So let's insert numbers, and there are only one ways to insert numbers into this diagram, which is given here as T1. But there are 2 ways to insert numbers into this diagram, which is here. And there is only one way to insert diagram into last diagram, and that's T4. Now, we will only construct the Specht modules of these first 2 Young diagrams, because you will see why. Now let's construct the Specht module of this standard Young tableau. Observe that the column group of T1 is just one trivial group, because the numbers are aligned in a row and there is no columns, basically speaking. And the basis elements will be just VT1, and this is just the tableau of T1. By definition, the Specht module will be spanned by this T1. So the vector space Specht module is just a one-dimensional vector space. Now, I want you to recall what W2 was. W2 was a subspace of U, and its basis element was this one. So let's consider this map. Let's map the tableau of T1 to the basis elements V1 plus V2 plus V3. Now, these both are vector space isomorphic. Why? Because they are just one-dimensional vector spaces. However, now we are not just talking about vector spaces. We are talking about modules, meaning that there is an S3 action on these vector spaces. So in order to see that they are also preserve the action, we need to check if action is preserved or not. Again, you have to check every element of S3, but I will just give an example here. Let's act on tableau of T1 by this 1-2 permutation. By the definition, this transposition can get inside, and we have this one. So this tells us that in the T1 tableau, 1 and 2 can permute, but this does not change anything in tableau formation because we just delete the vertical lines. Now let's act on V1 plus V2 plus V3 by 1-2 permutation. We obviously get the same vector. So S3 and W2 are actually CS3 isomorphic. Now let's consider this Specht module. Now we have 2 standard Young tableaus, which means that the Specht module will have a 2-dimensional vector space. Now let's consider the first T2. The column group of this T2 is just a cyclic group generated by 1-3 transposition, which can be seen here. And the column group of T3 is just a cyclic group spanned by 1-2, and you can see why here. Now, so by definition, these 2 elements will look like this. VT2 will be here, and VT3 is here. Now, I want you to notice these 2 relations. Let's act by 1-3 and 1-2 on these 2 vectors. We will get their negatives. But also, let's act by 1-3 and 1-2 to these vectors. We will also get their negatives. But do you remember what are those? Those were just the basis elements of W1. So if you consider this map, you will again get that this Specht module is actually CS3 isomorphic to W1. But realize that, recall that we said that we don't know if W1 is irreducible or not. But now we can be sure that it's irreducible. Why? Because it's isomorphic to a Specht module, and Specht modules are always irreducible. Now, let's finish our presentation by asking why do we need Young tableau at all? Because basically they give the dimension of irreducible modules. Moreover, they help the construction of irreducible modules. And actually, these two items are quite hard processes. But as you've seen through the whole presentation, the Young tableau, the notion of Young tableau, facilitates our job very much. But the more is true, inductively, we can construct SM modules for bigger n too. Now, today, we just work with n equals 3. We were here. But if you go on to the next level, for the you want to work with S4 modules, you just take one empty box and you just add this empty box to the Young diagrams over here, and you just get the other irreducible modules of S4. And I want you to add that the Young tableau and the representation of symmetric groups are still studied. And for those who are interested, I just leave here some further readings, 2 books and 1 paper. So that's all for me today, and thank you all for listening.
Teşekkür ediyoruz Övünç.